Okay, students, Assalamu alaikum. Let's start with our lecture today. Previously, we were discussing about different pressure measurement devices. So first we discussed uh, piezometer tube. Piezometer tube is one measurement device, but it has certain disadvantages, limitations, which we discussed before. In order to overcome those limitations, we come up with another device, which is basically similar to piezometer tube, but just make it a U-tube. So we call it U-tube manometer. And we place a manometric fluid in it so that now we can also measure the pressure of the gases. Now let's talk about differential manometer. Differential manometer is to overcome one another issue. And the issue is that if the pressure is very high within the pipe, even whether it is a U-tube manometer or it's a piezometer tube, we need a very long tube. Why? Because when the fluid is going to enter from the main pipe into the piezometer tube or the U-tube manometer, it's going to push the fluid to a very long distance. Okay, so in that case, it's not practically feasible to use either of the two devices because both of the devices are open to the atmosphere, and our comparison always is then with the atmosphere. But sometimes we have very high pressures within the line, and we just want to know that what is the pressure difference between 2 points in the line. It's possible that both the points are at a very high pressure compared to the atmospheric pressure, but we are not concerned that how much is the actual amount of pressure at that point. We just want to know that I have 1 point in a line, I have another point in a line, and between the 2 points, what is the difference? I'm just concerned, what is the difference between the 2 points? In that case, we can use the differential manometer. So differential manometer can be connected, again, it's by the pipe, simple pipe. Okay, so we have a simple tubing, we can connect it, or let's say this is the main pipe. Let's say this is the main pipe and the main flow is within the main pipe. So we can make 2 taps and we can make a connection between the 2 pipes using a manometer. We put a manometer fluid in between. Okay, so what will happen is that the fluid is going to enter within the differential manometer, and it's going to push the differential manometer fluid on one side. From the other side, also fluid is going to enter into the differential manometer. Okay, so their pressures are balanced together, and only the difference between 0.1 and 0.2 is going to be reflected in the manometer fluid. Okay, so the actual in reality, the overall pressure of the fluid is balanced at the 2 ends. Okay, and only the difference between 1 and 2, how much is the difference between 0.1 and 0.2 is going to be reflected in the manometer fluid. Okay, so we will just know that what is the difference without knowing what is the actual pressure at 1, what is the actual pressure at 2. Okay, so it's like saying that one person has 5 rupees more than the other person. We're just going to know the difference. We don't know how much one person has in actuality and how much other has in actual. Okay, so if maybe one has 1,000, the other has 1,005, maybe one has 100, other has 105. We don't know how much is the actual. We are not concerned with how much is the actual. We're just concerned what's the difference. Okay, so this is how it is. This is how it works. It eliminates the limitation that if the pressure is very high within the main pipe, if the pressure is very, very high within the main pipe, then normally we cannot use piezometer tube or U-tube manometer. Why? Because on the other end of the tube, we have atmospheric pressure. If the pressure is very high compared to the atmospheric pressure, you need a very long tube for the piezometer or for the U-tube manometer. But for this differential manometer, it does not matter how high is the pressure compared to the atmosphere, because we are not comparing with the atmosphere at all. Both the ends are connected with the same pipe. Okay, so we are just going to find out how much is the difference between the 2 points in the main pipe, just the difference. So we are not comparing with atmosphere at all, so it does not matter how high is the pressure within the pipe compared to atmosphere. Okay, so this is the disadvantage of the previous two, which has been eliminated in this differential manometer. Okay. Again, our methodology would be the same of finding out the equation. Okay. Let's have a look here. We want to develop the equation. Suppose we want to find out P2. Okay. So we will start from the known point. Suppose the known point is P1. Okay. So it should be P1. Then we are moving down. We are moving down. And how much down? We move down a distance of, let's say, del y. Okay. Del y distance we move down. So plus gamma of the main flow. I will write here F means the main flow. Okay. Gamma of the main pipe into del y. Then we are moving further down until we reach to the manometer fluid. Okay. So let me do like this. Take bracket plus del y plus how much we go down further? Del h plus del h. Okay. This is for the same fluid, main pipe fluid. Then once we reach this point, now we can now we can make a jump directly from here to here, because horizontally the pressure remains same. Okay. So now after moving from this point, now we are moving back up. Okay. So when we are moving up, so negative, now this time gamma of the manometric fluid. This is the manometric fluid into del h. Okay. Plus, no, again minus, because we are moving up. So now we are at this point. So we can move from this point till here. Okay, so minus gamma of, again, the main fluid, okay, into del y. Okay, so now we have reached till this point here. Okay, now we are moving further up till point 2. Okay, so again minus gamma of the fluid. Okay, and how much is the distance? This is distance is Z2 minus Z1. Okay, so Z2 minus Z1, and this thing is equals to P2. Okay. So you can see here P1 plus gamma A, they have said this is fluid A, this is fluid B. So gamma A in del Y plus del H minus gamma B del H minus gamma A del Y. Okay, they have just combined these two together. Del Y plus Z2 minus Z1. This thing is equals to P2. So you can generate the equation for the differential manometer correspondingly. Okay. Is this equation clear? Generation of the equation? We are just following a simple law that we start from one point, and mostly the point should be the one for which we know the pressure. We start from one point, and then if we move down, then it's plus gamma H. If we move up, then it is minus gamma H. That's it. Okay. So this is the same equation developed, which I have developed here above. Now this is just rearranging the same equation, in this format. Okay, now here P1 plus gamma Z is the piezometric head, piezometric pressure. This is piezometric pressure at 2, piezometric pressure at 1, piezometric pressure at 2, and it could be written as like this: piezometric pressure difference into gamma B by gamma A minus 1. It's okay, you can write it in this format, you can keep it in the original format as done before, but both are okay. Okay, so now we have, okay, in case of differential manometer, a problem related to the differential manometer, if it comes, then this formula will be provided to you in the exam, okay? Without the description that what is H1, what is H2, Okay, so you should know. The idea is that you don't need to memorize the formula, but you have gone through it, so you know what are the terms. Okay. So find the change in the piezometric head for the pipe flow. The a differential mercury manometer is connected to two pressure taps in an inclined pipe as shown in the figure, the previous figure, using the same figure. Okay. Water at 50 °F is flowing through the pipe. The deflection of mercury in the manometer is 1 inch. 1 inch is the deflection of mercury in the manometer. Okay. That is delta H here. Find the change in the piezometric pressure and the piezometric head between the 2 points. So we need to find this change. So this change can be found by simply this formula. As I told you, this formula will be provided to you in the exam. Okay. But I can also ask you to produce this formula because this formula is simply produced by using the main equation which we developed earlier. Okay. So you can also generate this formula. So there are both possibilities. Either I can provide you the formula and ask you to just plug in the values and solve the problem. Definitely. Then the diagram will be good. Okay, so here del H is known, given in the question. It's 1 inch. That's why I converted into feet. Okay. Then we have obviously gamma Hg will be provided to you, gamma of water will be provided to you, nothing else in here. Substitute the values, you're going to get that difference in the piezometric head. And once you have the difference in the piezometric head, just divide by the gamma of the main fluid so that you can find out what is the piezometric pressure. So this difference in the piezometric head multiplied by the gamma of water, because the water is there in the main, water is there as the main fluid in the pipe. So you're going to get the piezometric pressure, pound per square foot. Is it clear? Is there anything within the problem which is not clear? Okay, let's see this problem. What is the pressure at the center of pipe B? Okay, so here we have this is the case. So see here, let's first analyze. We have a small bulb here at the top, and this bulb is B. Okay, and the center of bulb is here. So from bulb, within this bulb, we have a fluid for which gamma is known. I don't know what fluid is it, but gamma is given for the fluid. Okay, so then this is 50 centimeter inside. After that, we have another fluid. This another fluid is also, I don't know which one is this, but the gamma for the other fluid is also given. Okay, so from A to C, it goes down 10 centimeter. Then after that, from C to D, it moves up, and here it is open to atmosphere. Here it is open to atmosphere. So now we need to know that what is the pressure here, PB. PB is something that I need to find out. Okay. Obviously, as the procedure that we have been following, always start from a point which is known and then move to the point which is unknown. Okay, so I will start from the point here, from point D. Why I will start from here? Because here it is open to atmosphere, so I know the gauge pressure will be 0. Okay, so I will start from this point. So I will write here PD. Okay, now I'm moving down, so it should be plus or minus? Plus. Plus. This is gamma fluid B, gamma B. Okay, that's gamma B. Multiply by, now we need vertical height. Here it is 50 centimeter, but this is 50 centimeters inclined. I don't want inclined. We need vertical height. So vertical height will be what? So this is the angle in the form of an angle. It is shown here, or like a right angle triangle. You have seen this in statics as well, in dynamics as well. If it is like this, then how we are going to find it? So it's basically, this is 3, this is 4, hypotenuse will be 5. Okay, so it should be 3 by 5. The fraction should be 3 by 5 if I want to know the vertical fraction. Okay, so it should be 3 by 5 of 50. This is a right angle triangle, right? Right angle triangle. This is 3, this is 4, this will be the hypotenuse, which will be 5. It's clear? So it should be 3 by 5 of 50. So this, now I have reached to point C. Okay, from D to C. Now I'm moving from C to A. So I'm moving up. So up means negative. So negative, but it's the same fluid. Negative gamma B. How much up? 10 centimeter up. Okay. So, okay, right now I'm writing here in centimeters. You don't have to write it in centimeters. It's better to convert everything into the basic SI unit and move it. There I'm just for explanation, I'm going through it like this. Okay. So I have reached to point A. Now I will move further up. So it's again negative, but this will be gamma A. And how much? 50. And this thing is equals to the pressure at B. Is it clear? I know what is gamma B. I know what is gamma A. Just substitute the values and I'm going to get the answer. So you can see here. Okay, what they have done is that I've done it in one step. They have done it step by step. Moved from A to B, then moved from C to A, then moved from C to D, then combine them all together, and then in the end you get what is the pressure at B. It's okay. You can do it in this way, or you can do it in one single step. Both are correct. Both are going to give you the same answer. So it comes out to be PB is equals to negative 1000 Newton per meter square gauge. That means it is vacuum pressure. So that means 1000 Pascal vacuum. So that's the solution of this problem. Is the solution here clear or not? Okay, so we discussed a few devices. Then there is another device, which is an electromechanical device, which is basically the pressure transducer. So pressure transducers are also used to measure the pressures. Okay, there is a specific components and configuration with the operation of this device written here. I want you to go through it yourself. There is no numerical content into it, just theoretical explanation of how this device is used to measure the pressure. Okay, so go through it yourself, descriptive forms. So then we are going to move towards the next topic, which is the hydrostatic forces on plane surfaces. Now, suppose if you have a fluid contained, because we are still in fluid statics, so we are not talking about the fluid in motion. But if the fluid is static, even then, if it is contained in a container, the walls of the container feels the pressure. Okay, there is a force of pressure of the fluid which is exerted over the walls. Okay, so now it depends upon the orientation and the shape and the size of the wall. If the wall is vertical, the wall is horizontal, wall is inclined, what is the shape of the wall? Based on that, we can actually find out that how much is the force applied. There are two things here. How much is the force, then where it is applied. Okay, obviously the resultant force will be applied at a certain position. Okay, but what would be that location? What would be the position of the force? Okay. So these are the things that we are going to look into the topic. Okay. So hydrostatic forces on plane surfaces. The most easiest is the horizontal plane. Suppose if I have a horizontal plane and the fluid is on the top of the plane. Obviously the fluid is going to be exerting pressure on the plane. Okay, so this will be uniform pressure distribution, because in the horizontal surface the pressure remains constant. Okay, so pressure variation is with elevation, not in the horizontal direction. So in the horizontal direction, since the pressure is constant, So there will be uniform pressure distribution, and so the uniform pressure will be applied here. Now the question is that how much or what is the location of this pressure? Okay, so the location of the pressure will be exactly the centroid of this plane. Okay, now the question is that, do you understand centroid? What is centroid? Centroid is the geometric center of anything. You see a geometry, right? Let's say this is a geometry. The center of it would be centroid. You see as geometry, center of it would be centroid. Geometric center. Now, why this is important? Because sometimes where does the weight of the body act? The weight of the body does not act on the geometric center. It acts at the center of gravity. Now, if the mass is equally distributed within the object, then the centroid would be the same as center of gravity. But there is a possibility that the mass is not equally distributed. Suppose if you have a balloon and you put a little water in the balloon. So the water will be on the downside of the balloon. The balloon is like circular, like spherical. But now the mass is not equally distributed. On the top you have air, on the bottom you have water. So the center of gravity would not be in the center. It will be shifted towards where you have more mass. So center of gravity would not act at the centroid. Centroid would still be in the center of the balloon because it is a sphere. Geometrically, it is a sphere, irrespective of how the mass is distributed. So the centroid would still be in the center of the balloon, but the center of gravity would not be there because the mass is unequally distributed. So the center of gravity normally shifts towards where you have more mass. Okay, so if the more mass is on the upside, the center of gravity will shift towards the up. If the more mass is towards the right, center of gravity is going to shift towards the right. And this is something you studied in before intermediate or in intermediate. How to find the center of gravity. I think you did also a practical in physics. How to find the center of gravity of any object. So you have an understanding that yes, center of gravity shifts with the mass. If the mass distribution is uneven, center of gravity would shift. Okay. So the point is that where will the line of action be? So the line of action where the force of the pressure will be applied. The force of the pressure will be applied at the centroid for the case of the horizontal surface. Okay. And the point where the force of pressure will be applied of the fluid, that point is known as center of pressure. So now you have another thing here, center of pressure. Center of pressure. Centroid is the geometric center. Center of pressure is the point where the pressure of the fluid is acting on the surface. If it is a horizontal surface, then centroid and the center of pressure both will be same. If it is a horizontal surface, then centroid of the object, of the plane, and the center of pressure, where the fluid pressure is going to be acting, they both are same. Is this point clear? Okay, look, you have, let's say you have a horizontal plane, okay? The centroid of the horizontal plane will be in the center. Now, if there is fluid above, let's say there is water above. So the water is going to be exerting pressure over the surface. What would be the location of resultant force where the pressure of water will be acting? The point where it will be acting, we call it center of pressure. And for the case of horizontal plane, centroid and center of pressure both will be same. It will be actually acting at the center, but only if it is a horizontal surface. If it is vertical surface, then no. Then the point where the point where the pressure of the liquid will be acting will not be the center of this thing. Why? Because pressure varies in vertical direction. So if it is horizontal direction, there was no variation in the pressure. It was uniform pressure throughout. But if it is a vertical or an inclined surface, then the pressure here is less, pressure here is more, here is further more. So now it's not the uniform pressure throughout. It cannot be at the center then. Is that clear? That's the main thing. So hydrostatic forces on plane surfaces. If the plane surface immersed in a fluid is not horizontal, then the hydrostatic pressure is linearly distributed over the surface. Okay, then it is not uniform. It's not the same. So pressure, force due to pressure at this point will not be the same as the force due to pressure at this point. Because this point is at a lower elevation, means the pressure will be higher. Okay, we discussed it in the last lecture that as we move down in a fluid, the pressure increases. Okay, the more we move up, the pressure decreases. Okay, so it will be linearly distributed, not uniformly distributed. Is this point clear? So if you look here, let's say this is the surface. Then the centroid of the surface would be the center. Centroid of the surface is the geometric center. But the center of pressure, where the force of pressure will be acting, will not be the centroid. But it will be at a point below centroid. And that makes sense. Why below? Because on the lower side, the pressures are higher. On the upper sides, the pressures are lower. Okay, so if the lower sides pressures are higher, obviously the forces will be higher on the lower sides. So the center of pressure, which is going to be shifting down the centroid. Okay. So the center of pressure, the location where the force of the fluid, force of the hydrostatic fluid will be acting for the case of inclined or vertical surfaces, where you have elevation difference. Okay, it will be below centroid. Centroid is the geometric center. Center of pressure will be slightly below the centroid. Okay, so that is the center of pressure. Now there is one thing which is a bit confusing, but you should understand this thing. When we are finding out, calculating the magnitude of the force, when we are calculating the magnitude of the force, we are going to use the centroid of that object. But once we calculate the magnitude of the force, this force will not be acting on the centroid. It will be acting on the center of pressure. So let me repeat again. For calculating the force magnitude, for calculating the force magnitude on, let's say this is the surface. Let's say I have this surface. If I want to calculate how much is the force acting on this surface, the magnitude of the force, I'm going to use the centroid. But once I have calculated the force, this force will not be acting on the centroid. It will be acting on the center of pressure, which is different from centroid. Okay. So normal observation or thinking is that if the force is acting on center of pressure, we should use center of pressure to calculate the force. No, we will use the centroid to calculate the force, but it will not be applied on centroid. It will be applied on the center of pressure. Okay. So this is the point to remember. Okay, so let us see, now we have one problem. We need to find out, one thing is clear, that if it is an inclined surface, if there is a difference in the elevation, okay, so the point where the force of the hydrostatic fluid will be applied, that point will be below centroid. This is clear. But how much below? Now we need to find a formulation to calculate how much below. Okay. So for this, let's analyze this picture. Okay. So we have this object. This object is inclined. Okay. And this object is immersed in the liquid. So it is inside the liquid. Okay. And this is the free surface. Free surface is a surface open to atmosphere. This is a free surface. Okay. Now, if we just have a look at it, this object is like this. The side view of the object would be like this. This is the front view of the object. Okay. Now, from the side view of the object, obviously the force will be acting. Force of the hydrostatic pressure would be acting like this. Okay. You see here, if we look at from the front view, if you look from the front view, this is the centroid. Centroid would be exactly in the geometric center of this object. Okay. The center of pressure would be here, slightly below. Okay. Now, if we draw, if we shift our axis, because this is an inclined surface, so we can shift our axis. Instead of having axis X and Y like horizontal and vertical, instead of having like this, we shift our axis to like this, that X is like this and Y is like this. Okay. So if we shift our axis X and Y like this, okay, so corresponding to that, our point of zero, our point of reference would be at the free surface. Okay. So if our point of reference is on the free surface, then Y bar would be the distance. I will say slanted distance. Slanted distance because it is not vertical, it's not horizontal, it is making a certain angle. So Y bar would be the slanted distance of the centroid from the x-axis. YCP is the slanted distance of center of pressure from the x-axis. Now YCP will always be greater than Y bar. This is something you should understand. Why? Because YCP is the center of pressure, and as I told you, center of pressure should be a little below than the centroid, because at the lower sides the pressures are higher. Okay, so one thing is very clear, that YCP should be greater than Y bar. Okay. So now, as I told you, when we have to calculate the magnitude of the force, we are going to use Z bar, not ZCP. Why was the slanted distances? Z is the vertical. That is the vertical distance. Okay. So instead of using the point of center of pressure, we are going to use the centroid to calculate the magnitude. Okay. So FP is equals to gamma Z bar A. We are using Z bar, not ZCP. Okay. Now the question is that how to determine. Okay, before moving towards the center of pressure, let's have a small problem to calculate the magnitude of the force. Okay, so that the problems make things much more clear when understanding the subject. Hydrostatic force due to concrete. Determine the force acting on one side of a concrete form, which is 2.44 meter high and 1.22 meter wide, means 8 feet by 4 feet, that is used for pouring a basement wall. The specific weight of concrete is provided. Okay, so first of all, you see, normally if you have seen how the concrete is poured, we make a form. You can say it's casing. We make a casing so that inside the casing we pour the concrete. and then that concrete solidifies. Once it is solidified, we remove the casing, so the wall is there. Okay, so this is how it is done. So suppose we have a case here that we make a casing. Okay, and this casing is basically known as concrete form. So this is your concrete form. Okay. Okay. Determine the force acting on one side of the concrete form. We want to know that how much is the force acting on one side. Suppose we are considering this side. Okay. Concrete, we will pour the concrete, or the concrete is poured here. So you put the concrete here. Obviously, the concrete is going to push the concrete is a liquid. Initially, it is liquid. Later on, when it solidifies, it becomes solid. But initially, it is liquid. So it is a liquid which is going to apply force, hydrostatic force on the walls. So we want to find out how much will be the hydrostatic force on one of the walls. Okay. On one side of the concrete form, okay, the concrete form is 2.44 meter high. So how much is the height? How much is the height? It is 2.44. Okay. And 1.22 meter wide. Wide will be into the paper, into the board. Okay, width will be 1.22 meter wide. That is used for pouring the basement. The specific weight of concrete is given. This is gamma. Gamma for the case of concrete. Okay. Now what do we need to find out? We need to find out the force. This concrete will be applying force on the wall. We need to find how much is this force. Okay. So we are calculating the magnitude of the force. We are right now not determining what will be the location of this force. We are just calculating the magnitude. Okay. Now, if you look here, the wall over which the concrete is going to be applying the force, this wall is basically a rectangle. This wall is basically a rectangle. And if I look here, it will be like this. This will be the height, 2.44, and width is 1.22, sorry, 1.22, right? Okay. So if you want to find out the force, so the force would be pressure into area, right? Force is basically what? Pressure into area. Okay, so that will be pressure into area. Okay, but the pressure we already studied that pressure is basically equals to rho gh or gamma h, right? Or gamma h. Okay, so I'll write here gamma h into area, right? Now this h would be the location of the centroid of this object. Centroid of the object from the free surface. Okay, so let's say that the concrete is poured at till the top. Okay, so centroid will be from where? From top to the center. So it is 2.44. So 2.44 divided by 2, that will be 1.22, right? Okay, so here this h will be 2.44 divided by 2. Okay, area will be what? 2.44 into 1.22. Okay, and gamma is given. So I will just substitute the values of gamma, h, and a, and I'm going to get the force. So you can see here, force is pressure into area. Pressure is gamma into z of centroid. So we are using centroid to calculate the force. So 23.6 multiplied by 2.44 divided by 2. This multiplied further by the area, which is 2.44 into 1.22. Okay, so we are going to get the force, hydrostatic force on the concrete. So problem is solved. Do you understand how we calculated the hydrostatic force of concrete on the wall? Anything which is not clear within the solution of this problem, please ask. Is it clear? So let's move ahead. Now finding out the other thing, location. That was one thing, that you find out the magnitude of the force. But the second point is that, okay, now this magnitude applied where? So obviously it will be applied at the center of pressure. But center of pressure for the vertical plane will not be the centroid. It will be below centroid. How much below? So finding out the location is now another issue that we need to find. Okay, so there is a small derivation, okay, which is done here to actually find out what is the formulation between center of pressure and the centroid. So basically the second moment of inertia, second moment of area is used here. Now you studied the second moment of area somewhere. Did you study second moment of area before? Yes. Second moment of area. In statics. Also in strength of material, you have used it. Whether you have studied it or not, but you have used it. And in the intermediate study also. So, but anyways, here right now, I'm not going to explain you what is second moment of area. This is another big topic if I have to go through it. So right now, there is no time to go through this thing. But presuming that you know it, and you're just shy to tell me. Okay. So I'm going to continue with this presumption. Okay, anyways. So after going through the derivation is there in the book. I've placed it on the in the slide as well. But I'm not interested in going through with the derivation with you guys. You can go through it yourself if you're curious, you know. Okay, so just going to look at the final formula. Okay, so the final formula is that YCP, Y is the slanted length, not the vertical. Vertical we call it as Z. Slanted is Y. Okay, so YCP, Y center of pressure, is equals to Y bar. Y bar is again the slanted height till the centroid, plus I bar divided by Y bar A. Now I bar is the second moment of area for this surface. If you have a rectangular surface, it is second moment of area for rectangular surface. A triangular surface, circular surface. We can have an oval surface, okay, elliptical surface, whatever the surface it is. The second moment of area of that surface is basically I bar. So I bar divided by Y bar. Y bar is again slanted height till the centroid. Okay, multiply by area of that surface. So this is the formula which link the centroid with the center of pressure. And so by this formula, you can find out what is the actual location of center of pressure. Once again, I would like to emphasize here, these are the Y's, slanted height, not the Z. Okay, the difference you can see here, these are the Y's. If I want to find out what is the Z, so Z would be the vertical distances. Okay, from this point till this point, it will be Z bar. From this point till this point, it would be ZCP if I'm finding out the verticals. Okay, okay, so the formula is in the form of slanted. So whatever be the angle of that object. Okay. This formula will be provided in the exam if needed in the numerical. This formula, YCP is equals to Y bar plus I bar divided by Y bar A, will be provided in the exam if needed in the numerical. The formula to find out the second moment of area, I bar, this will also be provided in the exam if needed for calculation in the numerical. Okay. But it will not be explained that what is Y bar, what is YCP. Okay, so this becomes a real problem for the students, because they presume that the formula is provided with an explanation that what are these terms. No, formula will be provided, but then there will be no explanation either written or provided orally about the terms used here in the formula, presuming that you have gone through the lecture and you know what are these terms. Okay, let's see a problem here, and that's going to actually clear the doubts which we have, which might be there in the understanding of the subject. Okay. Before going through the solution of any problem, the first thing which is very important is to understand the problem statement. What is asked in the problem? Understand the scenario of the problem. Okay. Force to open an elliptical gate. An elliptical gate covers the end of a pipe 4 meters in diameter. If the gate is hinged at the top, what normal force is required to open the gate when the water is 8 meters deep above the top of the pipe and the pipe is open to the atmosphere on the other side? Neglect the weight of the gate. Okay, so let's have a look at the. Okay, so you see here, there is, you can say, a water container, big water container. In the water container, you have a 4 meter diameter pipe going into the container. Okay, and the thing is that at the end of the pipe, a gate is there. This gate is actually closing the pipe. Okay, but the thing is that the pipe is circular. Okay, if I cut the pipe, at any point, this will be a circle. But if I do not cut it vertically, if I cut it at a certain angle, then if you look at it, it won't look like a circle. Then it would be an elliptical. If I cut it exactly or vertically, then it would be a circle. But if I do not cut it exactly vertically, if I put it in a tilt at an angle, then if you look at from the front, if you look at perpendicular to that cut area, you will find that it is now an ellipse. So it becomes an elliptical gate. If you put a gate there, then that gate will not be a circular gate. That would be an elliptical gate. The thing is that at the top of the gate, a hinge is there. At the top of the gate, here, a hinge is placed so that the gate can be opened and closed. Okay, so that's the point that's the point of rotation for the gate. So the gate can be opened and closed. Okay. So this is basically what 4 meter diameter pipe. Okay, this is open to atmosphere. Here we have atmosphere, and the water is there in the container, which is also open to the atmosphere at the top. Okay, from the top of the gate, the vertical distance is 8 meter. 8 meter is from where? From the top of the gate till the free surface. Okay, okay. This is 4 meter vertical distance, but after it is slanted cut, okay, so the gate length is 5 meter. Okay, so if I draw an ellipse here, so this is not a very good ellipse, but if I draw an ellipse here, then this distance is 4 meter and this distance is 5 meter. Okay, it's like this. So you see here, it's cut like this. So this is 5 meter and this will be 4 meter, because the actual original pipe was 4 meter. Since the original pipe was 4 meters, so the smaller diameter of the ellipse will be 4 meter. But the larger diameter of the ellipse here is 5 meter. Is it clear? So we have, this is the situation. So elliptical gate covers the end of the pipe 4 meter in diameter. If the gate is hinged at the top, what normal force is required to open the gate? Okay, if the gate is hinged here and I want to open the gate, I have to apply the force here to open the gate. If I apply the force in this direction, then the gate will be opened. Okay, so I need to find how much of this force is needed to open the gate. if I want to open this gate, how much of the force is needed to open this gate? Okay, this is what I need to find out. To open the gate, when the water is 8 meters deep above the top of the pipe and the pipe is open to the atmosphere on the other side, neglect the weight of the gate. So before moving towards the solution of the problem, first of all, do you understand the problem statement? What is asked? Do you understand the problem scenario? We have a pipe. This pipe is going in the container. The pipe is not cut vertically. The pipe is cut in a certain angle. So we have an elliptical gate. Elliptical gate is hinged at the top, and we want to open the gate. So obviously we will apply the force at the bottom of the gate. Okay. So this is the situation. Okay. So now we are going to, if you understand the problem statement and you understand the problem figure, then the next step would be, so we will move towards the solution. Is there anything within the problem statement and the figure that you do not understand? Please ask. Yeah, because you see here, this is the door. It is hinged on the other end. You want to open the door. Where will you apply the force? The other end. It will require more force. Exactly. The least force would be when the moment arm is the largest. The least force will be when the moment arm is the largest. That's why we place the point of the handle is placed opposite to the hinge. Problem statement clear? Okay, now let's let's go towards the problem solution. Now there are two things. First thing is that, okay, we know, let's have again look at the picture. First thing is that we know that there is water here. Because there is water here, so water will be applying hydrostatic force on the gate. So first of all, we need to know that how much is this force and where is it applied? I want to find out how much is the force needed to open the gate. But first I need to know how much is the force of water and where it is applied. Okay. Then I can determine that how much will be the force that I need to open the gate. Okay. So let's first go towards this problem. So we will look at each and everything separately, one by one. So first we are going to look at finding out the magnitude. I told you, for finding the magnitude, we are going to use centroid, not center of pressure. But the location where this magnitude will be applied will not be the centroid, it will be center of pressure. Okay. So first we are going to look at finding the magnitude. Okay. So finding the magnitude is F is equals to pressure into area, right? Pressure into area. Or I can write here gamma into Z. Instead of writing H, I'm writing Z. Gamma into Z into area. But this Z will be centroid, the center of it. Okay. One by one. Gamma, is it known? Water, it is provided in the question. So gamma is known, right? Area. Now, what is the area of this surface? Okay, so this is basically an ellipse. So I need to know the area of the ellipse. So I need to know the area of the ellipse, right? This is not a circle. This surface is an elliptical surface. So the formula for the elliptical surface area will be provided. Or whatever the surface, if the surface is a regular surface, rectangle, square, triangle, then the area will not be provided. But if it is an irregular surface, something which is not common, like an ellipse, then for that case, the formula for the area will be provided. Okay. And the formula for area here is basically pi into A into B, where A is smaller diameter, B is the bigger diameter. Okay. So since you know the smaller diameter and bigger diameter both, so you see here, this is the area of the elliptical panel, pi into A into B. Okay, so here A and B are the, sorry, not the diameters, they are the radiuses. The diameter was 4 and 5, so radius will be 2.5 and 2. Is it clear? So if you substitute the values, you're going to get the area. So formula will be provided to you, so that's not a big issue. Now finding out Z bar. Okay. Look here. Z bar is from the surface open to the atmosphere. So from this surface. Okay. So it would be in the centroid. Centroid means the center of the ellipse. Center of the ellipse will be where? It will be here. Right? It will be actually center of the pipe. It was this pipe, right? Center of the pipe. Originally the pipe is this. Okay. So I want to know this distance. That will be my Z bar. Is it clear? So what will be this distance? If this is 8 meter and this is 4 meter. No, not 8. 8 will be the top of this. But I want the centroid of this ellipse. The centroid would be the center of the ellipse, right? And here, this ellipse is coming out from this pipe. 10 pe aa jayega, exactly. So 8 and from here 2. 8 plus 2, that will be 10. Is it clear? Isme basically when you are finding it out, when you are finding out the pressure, okay, so we are using H, gamma H. This H is the vertical height. This H is the vertical height. Okay. So here, so you see here, pressure into area, pressure will be 9810 multiplied by 10. Do you understand this 10 here? Multiply by area. So you're going to get the magnitude. So the first thing is done. Now you have find out how much is the force of the water on this gate. And for finding the force of water on the gate, we did not use center of pressure. We use centroid. Till this point, everything is clear or not? I will move forward if you are okay till this point. This gamma ZA. Gamma Z was the pressure. Area, whatever the area of the surface for which we want to find out the force. Is it clear till here? Shall we move forward? Let's move forward. Okay. Now I need to know, okay, this is the force. 1.54 mega Newton is the force. But where it is applied? It is applied at the center of pressure. Now, where is the center of pressure? This is not a horizontal plane. If it was horizontal plane, then it would be exactly at the centroid. But this is an inclined surface, so it's not the center of it will not be the centroid. It will be center of pressure. So for this, I have to use this formula. YCP. Okay. Sometimes it is written like this. Sometimes you put Y bar on the other side. Then it will become plus. So YCP equals to Y bar plus I bar over Y bar A, or like this. Okay. But normally, actually, it is written in this way. Why? Because we just need to know how much is the difference between YCP. We know YCP will be below Y bar. But how much is this difference? That is 1. But now here, these are the Y's, not Z. So these are the slanted heights. These are the slanted lengths. Okay. So that's why you have to keep that in mind. Okay. Okay. First of all, let's talk about area. Area, not an issue. Area is done. That's the same area that you use. Okay. Y bar also not an issue. No, Y bar is an issue. Let's look at the Y bar first. Okay. Because previously we were talking about the Z bar. Now let's talk about the Y bar. How much will be the Y bar? Okay. If I say that, let me just rub it first. Okay. If I say this is the center, So from this to this will be my y bar from here till here. This will be my y bar, slanted height. Okay. Now this thing is very clear. This thing will be how much? 2.5. What about this distance? Sorry, not till here. It will be because our free surface is here. Okay. Free surface is here. So till this point. Let me just erase. Is it clear? So how much is this distance? Okay, this is 2.5. What about this? Okay, now it's up to you. The way it's a simple question of mathematics. You want to do it the way you want, Pythagoras theorem, whatever. But I'm using a simple logic. When this is 4, this is 5. So if this is 8, this will be 10. Double of 4 is 8. So double of 5 should be 10. I'm just using a simple logic. Okay. When the vertical was 4, the slanted was 5. So if the vertical is 8, slanted should be 10. Simple logic. Okay. So I know this is 10. And this is 2.5. So 10 plus 2.5, 12.5. So my y bar will be 10 plus 2.5. So that will be 12.5. Is it clear? So y bar is now also clear. See here, 12.5. Okay. Look, 2.5 clear हो आपको? Now only thing is that 10 अभी clear नहीं है कि 10 कैसे आया? Okay. Now you want to find this distance. How much is this? But you know the vertical is 8. Exactly from the free surface to the center of this ellipse in the on the inclined plane, not vertical. Clear? Clear? Okay. So now let's talk about I bar. Now I bar is the second moment of area, but it will be for the ellipse. And I told you that in case if whatever the question you have in the exam, for that surface, second moment of area formula will be provided to you. Okay. So here the formula is pi a cube b upon 4. Okay. So a is 2.5, b is 2. These are the radiuses of the ellipse. Okay. So a is the radius of the larger side, b is the radius of the smaller side. Okay. So if you substitute the values and you know the formula, you can find I. So I is also here. Y bar is something you know. We have just discussed Y bar. So if you substitute all the values, you're going to get what is YCP minus Y bar. So YCP minus Y bar is 0.125, means on the surface of the ellipse, YCP is 0.125 below Y bar. Is it clear? Okay. So if you look here, this is the situation that we have, that this is the elliptical gate. It is hinged on this end. It is here we have to apply the force that I want to find out. There is the force of water. Okay, force of water which is applied here. Where is how much is this force of water? Hydrostatic force. It is 1.4 meganewton, which is applied here. And this is applicable at the center of pressure, not the centroid. Center of pressure. This is CP, center of pressure. Okay, centroid was this. Okay, and the centroid was from the hinge. It was 2.5. So center of pressure will be 2.5 plus 0.125. So that is basically 2.625. Okay. So this is basically 2.5 plus 0.125. So that is 2.625. So this will be this distance. Now I can find out this force very easily because I can find out, uh, I can apply the momentum equilibrium at the hinge. Okay, so the moment of the hydrostatic force will be this force multiplied by the moment arm, and moment of the force that I want to calculate will be this force multiplied by the moment arm, and they both will be opposite. So we can actually find out how much is the force needed. So if I take the summation of moments, moment equilibrium at hinge, so it will be 1.541 into 10 power 6 multiplied by 2.625 minus F multiplied by 5, because this was 5 meter, this elliptical gate. So we'll find out this force comes out to be 809 kilonewton. So 809 kilonewton is the force needed to actually open the gate. Do you understand the problem? The problem is done here. First, we find out magnitude by using the centroid. Then we find out the center of pressure so that we know the actual location where this force will be acting. And then after that, this is a simple problem then, finding out how much is the force needed to open the gate. Solution is done here. Is there anything within the solution which is not clear? This is not easy. But if you follow through the lecture properly, you won't feel difficult. Let's talk about hydrostatic forces on the curved surfaces. Now we did for the plane surface. So for the plane surfaces, horizontal or plane surface curve, you guys are a little tired. I want a break. Okay, let's have a break. 10 minutes tops. Okay, we'll be back in 10 minutes. Okay, so now we have already done the hydrostatic forces on plane surfaces. Now we are going to discuss about if we want to find out the hydrostatic forces on curved surfaces. For the case of curved surfaces, it becomes a little more complicated in the sense, what we do is that we find out the forces over the projections. So for a curved surface, suppose this is a curved surface, what we'll do is that we will find out the projection, horizontal projection of the curved surface, and we'll find out the vertical projection of the curved surface. Then, assuming that this surface is replaced by these projections, we find out the hydrostatic forces, horizontal and vertical. However, still there is some part of the fluid which we have missed, and that is because of our of our assuming projections. We have a certain volume of fluid which we have eliminated. Then we find out the specific weight or the weight for this volume separately, okay, and then add it up towards our main calculation. So this makes up a little complicated. For the case of the horizontal force, horizontal hydrostatic force, there will be no effect. But in the case of vertical hydrostatic force, there will be effect. Why? Because the weight of this unit is also acting downward. So then we have to apply the lever rule to find out the corresponding position of this force, vertical force. The best way to solve a problem is the best way to understand a concept is to solve the problem related to it. So let's start by solving a problem. Okay. Okay, let's first read the problem statement. We have a surface AB. This is the surface AB. It is a circular arc. That's a circular arc with a radius of 2 meters. So the radius of this arc is, this radius is 2 meters. Okay, and a width of 1 meter into the paper. Inside, in the Z direction, or you say going into the paper, it's 1 meter. So it's basically like this. So it's circular, but here, if you look from here, it's 1 meter into the paper. Okay. The distance EB is 4 meters. This is the distance EB. This is E. This is B. So here it is 4 meters. The fluid above surface AB is water. This fluid above, this is water. And atmospheric pressure prevails on the free surface of the water and on the bottom side of the surface. So bottom side, here we have atmospheric pressure, and the free surface of the water, here we also have atmospheric pressure. This symbol, see this symbol here, this symbol denotes free surface. So whenever you have this symbol, it is a representation that we have a free surface here open to atmosphere. Find the magnitude and line of action of the hydrostatic force acting on the surface area. So we know that there is water here, so obviously water will be exerting hydrostatic force. We need to find out how much is the magnitude of this force, and we need to find where it is acting. Okay. Here this is 2 meters because this is the radius of this. Okay. So this is 2 meters. Okay, before moving towards the solution of the problem, the first thing is you need to understand what is the problem question and the diagram corresponding. Is the diagram and the problem question clear or not? We need to find the force and the location of the force, hydrostatic force. And this is a curved surface. Is there anything within the diagram or the problem statement which is not clear? If this is clear, then we will move towards the solution. Okay, so let's move towards the solution. Okay, now the thing is that what I've told you is that in case we have a curved surface, what we do is that we find out the hydrostatic force over horizontal and vertical projections. Okay, so we are going to find out, let's say this is our curved surface. So we are going to make a projection here. This is the horizontal projection. Over the horizontal projection, you will have vertical force. Okay, this is the vertical hydrostatic force. Then you will have here the vertical projection. Over the vertical projection, you will have horizontal force. Okay, so we are going to find out the hydrostatic forces, vertical component and horizontal component. And if we do this, that means we find out the hydrostatic force for this water. Here still we are not considering this. We are excluding this, okay, which we are going to add up later on. Okay, so let's forget about this thing first. Okay, just forget about this thing. Just consider that you have a problem like this. Okay, and we solve first for this one. Do you understand what we are going to do? Okay, so equilibrium in the horizontal direction. So if when we are finding out the horizontal force, so that's on the vertical projection. Okay, so FH, again it will be P into area, which is equals to gamma into Z bar into area, right? Let's have a look at the area. Try to suppose you are standing here and you look from here. So how would it look like, this projection? It will look like a rectangle. We're talking about the projection. It will look like a rectangle, and this height will be 2 meters. This is 2 meters because 2 meters is the radius. So this will be 2 meters, and into the paper is 1 meter. Right? So 2 by 1 meter. You will have, if you're standing here, you will look at it like a rectangle, which is 2 meters on this side, 1 meter on this side. Did you open the recording? Yes. So is it clear? So area will be 2 by 1. That will be the area. So 2 meter by 1 meter is the area. Is this in clear? Area is done. Okay. Now let's talk about Z bar. Z bar is from the free surface. The free surface is at the top. Okay. So here, if you look here, this is 4 meter. And here, if you look here, this is 2 meter. But the centroid of it would be in the center 1. So 4 plus 1, 5. Okay. So this is 5 meter. Done. This is gamma 9810. So horizontal force on the vertical projection will be 98.1 kilonewton. Is this thing clear? Now let's try to figure out the vertical force on the horizontal projection. Okay. Again, same thing that we have P or right here, gamma Z bar area. Okay. So now look here, suppose if somebody is standing here and you're looking in this direction. So how would it look like a projection? Again, a rectangle. Okay. Where this would be 2 meter and into the paper is 1 meter. Okay. So it would look like exactly the same. Again. Okay. So 2 by 1 is the area. Okay. Now what would be Z bar? This is a horizontal plane. So centroid and center of pressure would be the same. So it will be just from the top surface for 4 meter. Right. So see here, 4 meter will be Z bar. Then we have gamma here. To substitute the values, you will have the vertical force. Is it clear? The vertical force component, horizontal force component is now done. But we are still missing something, and which is the specific volume of water which we ignored. Okay, so this specific volume of water which we ignored, now we have to consider that as well. This is specific volume of water. Okay, so it will be what? The weight of this water which we are ignoring. Okay, so weight of this water will be, weight is equals to mg, which is equals to density into volume into g, right? Mass is density into volume. Now density into g is gamma, so it's gamma into volume, right? Now wherever weight is going to come, I'm going to write, instead of mg, I'm going to write gamma into volume, and now you have to remember it. I don't have to go through this derivation again and again. Okay, so weight is equals to mg, which is also equals to gamma into volume. Okay, gamma will be here for the water, and volume will be the volume here. Now how much is this volume? It's basically a quarter circle. This is a quarter circle multiplied by the width into it. Okay, that's this thing. Quarter circle multiplied by the width. Okay, so circle area is basically what? Circle area is pi r square. So quarter circle will be pi r square by 4 multiplied by the 1, which is the width. Okay, so if you look here, pi r square by 4 multiplied by the width multiplied by gamma, this is going to give you the weight. So that will be 30.8 kilometers. In reality, this weight will be acting in the direction of vertical horizontal force, vertical hydrostatic force, FV. So it will be, in reality, the total force will be added up here. Okay, so we have the horizontal force is 98.1, but the vertical force will be weight plus FV, which will be 109.3 kilonewton. Till here, everything is clear or not? We have found out the forces, okay, but we have not yet figured out what would be the exact location of the forces. Okay. Okay, so let's try to find out the line of action. Okay, for the case of the vertical force, FV, we don't have any issue because FV, we know where it is will be acting exactly at the center of this. Okay, because it is the horizontal surface, horizontal projection, horizontal surface, exactly at the center, centroid. Okay, but for the case of the vertical, it will not be at the center. It will not be at the centroid. It will be below centroid. So it will, we have to find YCP. What will be YCP? Okay. So for the case of the horizontal, we need to find YCP. So now look here. This is the formula for YCP. As I told you, this will be provided to you in the exam. Okay. Area will be for the projection. 2 by 1. Clear? Okay. Y bar was 5. 4 plus 1. Right? 4 above this curved surface, and this projection was 2 meter, so 2 half of this, the Y bar. Okay, so this is 5, so 5 Y bar. Okay, now I bar, I told you it will be provided to you in the exam, the formula, because here the projection is a rectangle, 2 meter by 1 meter. Okay, so for that rectangle, it is basically if we say this is A and this is B, so it's basically AB cube upon 12. And this formula for the second moment of area will be provided to you in the exam for the case of whatever needed in the question. Okay, so this is provided to you, so just plug in the values and you're going to get the value of I. Substitute all these values, you're going to get YCP. So YCP is 5.067. Y was 5. So it is basically 0.067 below the centroid. Okay. So now we have figured out for the case of the horizontal component of the force, what will be the exact location of the application of the force. But for the case of the vertical component, now we have to use the lever rule. Why? Because there are two vertical forces and both are acting at different points. Why? Because look here, for the case of the vertical force, vertical hydrostatic force, it is acting exactly at the center of this projection. But we also have a weight. Where will the weight will be acting? Weight will be acting at the center of gravity of this quarter circle. And the center of gravity of the quarter circle is not the same point here. Okay, so if you have a circle, the center of gravity would be in the center. But if you have a semicircle, the center of gravity would not be here. It would be somewhere here. And if you have a quarter circle, center of gravity would be somewhere here. Right? So weight location, it will be acting downward, but at a different point, not the same point as FB. Okay, so we have to, for this, the formula will be given that what would be the centroid for a quarter circle. The centroid for a quarter circle is this 4r over 3 pi. Again, this formula will be given to you in the exam, that if you have a quarter circle, what is the formula for the centroid of that quarter circle? It will be given to you in the exam. So we can actually find out, if we know the radius, we can find out that what would be the specific distance, okay, from the origin of this thing. Okay, now we need to find out what would be the resultant vertical force. We know the resultant vertical force will be summation of vertical component plus weight, but these two are acting at different points. So resultant force will be just the summation of these, but where it will be acting? Will it be acting here or here? No, it will neither be acting here nor be acting here. It will be acting somewhere in between. Okay, so that we need to find. We do it by we call it lever rule, or we can also use the we can also say the summation of moments. Okay, so it is this. Okay, so we can take the summation of moment at the origin point of this quarter circle. Okay, so if this is your quarter circle, okay, so on this quarter circle, we need to know that where is the center of pressure, x component of the center of pressure. Okay, we need to find out what is the x component center of pressure. This is what we need to find out, xcp. Okay, Fy will be the total force, which is this 109.3 kilonewton. That is Fy. Fv is the vertical component. There is a vertical component. Fv is here. Fv is here. Weight, we have just found out weight is here. Okay. So Fv will be the moment arm for Fv if you are taking at this point, if you are taking the moment at this point. So moment arm of this Fv will be 1 meter. Okay, because Fv was acting exactly in the center. So moment arm will be 1 meter. For the case of the weight was acting somewhere here. Okay. Okay, and we already calculated that how much is the x distance from the origin. So it will be 0.849. So weight multiplied by 0.849. Okay, weight was acting somewhere here. Okay, and this Fy is the total force, but where it would be acting, we can now find it out, xcp. Okay, so if you calculate, it comes out to be 0.957. Okay, somewhere in between, as I told you. Okay, weight was acting here, Fv was acting here. Fv was acting at 1 meter distance, weight was acting at 0.849. So the Fy will be in between weight and Fv. Okay, so this is 1, this is 0.849, and Fy is 0.957. Very close to Fv, but not exactly at the same point. Okay. So xcp will be this. Xcp is the center of point, x component of the center of point. Okay, for this. So now we have found out the location. X component of the location, y component of the location, okay, as well as the x component overall, y component overall for the hydrostatic force over the curved surface. Is this thing clear or not? Anything within the solution here which is not clear, please feel free to ask. Okay, we can have different kind of problems for the case of hydrostatic forces on curved surfaces. Suppose if we have a situation where we have the surface is submerged into this curved surface, into the water, then in that case, what we are going to do is we are going to find out the weight of this whole water on this surface. Okay. Suppose if we have a situation like this, then we have to find out the weight of if there was water here, again on this surface. Now in this case, the curved surface is submerged from below. The previous case, if it was submerged from the above. Okay, so we have to find out the weight. Obviously, the direction of the force, hydrostatic force, will be different. Okay, let's see this problem. Hydrostatic force on curved surface. The surface AB gate is a half of a circular cylinder with a radius of 10 meter and a width of 1 meter into the page. Now this time, previously it was a quarter circle, now it is a half circle, but again 1 meter into the page. Okay. A plane surface AC is connected to half circular cylinder and extended 5 meter above the half cylinder. So you have a plane surface here connected to this. Okay. The height of the water above point A is 10 meter. So this is point A. The height of the water above is 10 meter, 5 meter plus 5 meter. Okay. Atmospheric pressure prevails on the free surface of the water and on the right hand side of the gate AB. So here we have atmospheric pressure, here we have atmospheric pressure. Okay. Calculate the magnitude of the reaction force needed to just start opening the gate. Okay. So here, this is the pivot point. So here it is hinged here. So if we want to open this circular, semicircular gate, we have to apply a force here at this point. Okay. So if you apply the force at this point here, eventually the gate will be opened. But it has to overcome the hydrostatic force. Okay, so the hydrostatic force of the water is acting to close the gate. So it has to overcome this hydrostatic force in order to open the gate. Okay, so we need to find out how much is this force needed. Okay, but in order to find out how much is this force needed, first we need to know that how much is the hydrostatic force on the gate and where this hydrostatic force is acting. Then we can apply the moment at the pivot, which is our hinge here. And then we can find out what would be the reaction force. Okay. So again, because it is a curved surface, what we are going to do, we are going to take the horizontal and vertical projection. And by solving over the horizontal and vertical projection, we can actually find out the horizontal and vertical component of the forces. Okay, let's now, because we have already solved two problems with the same pattern. So I'm going to be a bit fast in this problem, considering that you have already gone through them with the understanding. Okay, so horizontal pressure on the force will be P into A, which is gamma y bar into A. Okay, so gamma is 9810, y bar will be 20. Okay, why it will be 20? So you can see here, this is 10 meter radius, so 10 meter will be this, and 10 meter above. So 10 plus 10, 20. So it will be 20. And then the projection will be what? Because it is because it is from this side, it is semicircle, but then it is 1 meter into the page. So if you are standing in front, it would look like a rectangle. Projection would look like a rectangle. 20 meter will be the height, which will be the diameter of this semicircle, and 1 meter into the page. Okay. So that's 20 into 1. If you substitute the values, you're going to get the horizontal force component. Okay. For the case of the horizontal force component, you have to also find the center of pressure. It will not be the same as the centroid because it is vertical. Okay. So it will be y bar plus I bar over y bar into A. Now y bar is clear, 20, 20, which we have already discussed. Okay. Area will be 20 by 1. We are talking about the projection. Okay. And I bar will be, again, projection is a rectangle. So AB cube upon 12, the formula will be provided to you for I bar in the exam. Okay. So if you substitute the values, it comes out to be 21.667. So at 20 is the centroid, and further 1.667 meter below is the center of pressure. Okay. So center of pressure is 1.667 below centroid. Okay. So that's about the horizontal component of the force. For the vertical component of the force, we have to just find out the weight of the water above it. Weight of the water above it. Okay, so vertical component of the force will be the weight. And as I told you, weight can be written as gamma into volume. I don't have to explain it again. Okay, so gamma is 9810. Volume will be what? Volume of this is half of the circle multiplied by the depth inside. So circle is basically pi r square. Half of the circle will be pi r square by 2. Multiply by the depth, which is 1 meter, substitute the values, you're going to get FV. So once you have FV, now you also need to find out where this would be located. Okay, because if it was a complete circle, then it would be located exactly in the center. But this is not a complete circle. This is a semicircle. So it will not be located in the center. It will be located somewhere here. Okay, so it will be actually 4r over pi 3. Again, this formula will be provided to you in the exam. The centroid of the semicircle, centroid of half cylinder. Okay. So you just substitute the value, you're going to get the x value here. Now, once you have this thing, now you have x component, y component of the forces available with you. Okay, the only thing that you need to know now is what is the force R needed here to open the gate. So now we can take the moment at the hinge. which is here. Okay, so r multiplied by this distance, r multiplied by this distance, this is the moment arm. So this was 5 and this is 20. Why? Because 10 is the radius. So that's r into 25 plus horizontal force. Horizontal force is here. Okay, and if you remember, we said that 20 is the centroid. Actually 10 is from here, it is 10, and then 10 and 5 is this. Okay, so if you are, when we are taking it, okay, we found YCP from the top. Okay, so YCP from the top was Y from the top will be 30, because you see here, this is 5, 5, 10, then 10, 20, then 10, 30. So 30 will be from the top of the surface to the pivot point. Okay, and YCP is acting below CP. Okay, so YCP was from the top, comes out to be 21.667. So it will be 30 minus 21.667. Why? Because we need to find it. We need to find this distance. If YCP is Y horizontal acting this, so we need to find this distance. So this distance will be total distance minus YCP. Okay, so it will be 30 minus YCP. So this is the horizontal component of the force. For the case of vertical component of the force, we have this distance multiplied by XCP. So if we substitute this, okay, you see here, this is plus and these two are minus. Why? Because you can see here the kind of moment. R is making a moment which is counterclockwise, and FH is going to make a moment which will be clockwise, and FV is going to make a moment which is also clockwise. So FV and FH are both going to make clockwise moment, and R is going to make counterclockwise moment. So we can find out, once we solve it, you're going to get the value of R. So it comes out to be 1.5697 times power 6 Newton. So far, everything is clear. I'm not saying it's easy. I'm just asking, is it clear or not? It is clearly difficult, sure, but clear. Okay, so let's move over to the next topic, which is buoyancy. Again, buoyancy is something which you have studied before, I think in the undergrad level as well. I mean, before during your metric or intermediate, you have studied. So buoyancy is based on Archimedes principle. Now, Archimedes principle is what? मैं वो सिंपल वर्ड्स में बोलूं ना, कोई घुसपैठिया आ गया ना तो उसको निकालना होता है बाहर, ठीक है? So this is what the water is doing. You have a water body, something came into the water body. Obviously, the thing that came into the water body has a volume, so it will displace some of the volume of water. Now that volume of water which is displaced, now it starts fighting. Okay, I want to go back in, you go out. This is what is happening. Okay, so you have this is, let's say this is a container and it was filled with whatever the water you had. Okay, something, let's say this is the object. Now it goes into the water. Okay, so what will happen is that it's going to displace some of the water. Okay, so the water level will rise. Water level will rise. Why it will rise? Because it will displace some of the volume of the water by going into it. Now this water level that has been displaced, okay, this is going to produce a buoyancy force to push this thing out. So the buoyancy force is in the direction so that the thing which has entered into the water goes out of the water. Okay, so it is in the direction opposite to the to the gravity. Gravity is always going downward, the buoyancy force is always going upward. Okay, because something has entered into the water and it has displaced some of the water. So how much of this force will be? This force will be depending upon how much water has been displaced. Okay, so this force will be equal to the amount of displaced water. The force applied by the amount of displaced water. And so this thing is, so this is basically the Archimedes principle. For an object partially or completely submerged in a liquid, there is a net upward force, buoyant force, equal to the weight of the displaced fluid. Not equal to the weight of the object, equal to the weight of the displaced fluid. जो फ्लूइड बाहर निकाला गया है इस ऑब्जेक्ट में, वो फ्लूइड का जो वेट है उसके इक्वल टू फोर्स अप्लाई होती है ताकि इस ऑब्जेक्ट को बाहर निकाला जाए वाटर से. सो इट्स बेसिकली जो घुस बैठ गया है उसको निकालना है बाहर. ठीक है, दिस इज व्हाट इज हैपनिंग एंड दैट इज द आर्किमिडीज प्रिंसिपल. इज आर्किमिडीज प्रिंसिपल क्लियर? ओके, द क्वेश्चन दैट कैन कम इन द एग्जाम, that is a conceptual question. Buoyancy is based upon which principle? So the answer will be Archimedes principle. And what is the statement of Archimedes principle? You could be asked in the exam that write down the statement of Archimedes principle. So you have to memorize the statement of the Archimedes principle. Is it clear? Okay, the formula for the buoyancy force is very simple. First of all, I will write here FB because it is the buoyancy force. And this thing is equal to the weight of the displaced liquid. If that liquid was water, then it would be weight of the displaced water. If that liquid was alcohol, then it would be weight of the displaced alcohol. If that liquid was oil, it will be weight of the displaced oil. If that liquid was mercury, that will be the weight of the displaced mercury. No relation with the object, with the weight of the object which has displaced this fluid. आप चाहे लकड़ी डालें, चाहे आप लोहा डालें, चाहे आप प्लास्टिक डालें, इससे कोई फर्क नहीं पड़ता. The only thing important here is that which fluid has been displaced. According to the weight of that fluid, buoyancy force will be acting. Is it clear? Okay. So buoyancy force will be equal to the weight of the displaced fluid. And I told you weight can be written as gamma into V. Okay. And weight is mg, but I have shown you the derivation how mg is equals to gamma V. Okay. So weight can be written as gamma into volume. And Vd is volume of the displaced. This is the simple formula for the buoyancy force. Do you understand the buoyancy force, the principle which it is based on, the statement of this principle, and the formulation to calculate the buoyancy force? Some remarks about the weight of an object. The weight of an object in a fluid medium refers to the tension in the spring when the object is attached to a spring balance. The weight registered by the spring balance depends on the medium in which it is measured. The weight commonly referred to in daily use is the weight of the object or body in air. Basically, अगर आपका वजन ज़्यादा है तो आप एक स्विमिंग पूल में जाएं और वेइंग मशीन को स्विमिंग पूल के अंदर डालें और स्विमिंग पूल के अंदर खड़े हो जाएं और फिर वजन करें, बहुत कम आएगा वजन. लिटरली अब 100 kg के हैं तो 50 kg भी नहीं आएगा शायद. What is the reason? The reason is that weighing balance जितना ज़्यादा weight आपका bear कर रहा होगा, according to that weighing balance जो भी measurement देगा. जब आप when you are standing in water, तो आपने कुछ water को displace किया होता है, तो वो जो water displaced होता है ना, वो एक buoyancy force against apply कर रहा होता है against the weight. तो उतना तो आपका वेट ऑलरेडी बायंसी फोर्स ने पकड़ा हुआ होता है. तो बाकी जो वेट है जो बायंसी फोर्स ने नहीं पकड़ा हुआ, वो बेसिकली आपका वेइंग मशीन बेयर कर रहा होता है. So that's why when you are standing in the liquid, in water, in the swimming pool, and if you weigh yourself, it comes out to be quite less. Okay? Because some of the weight is countered by the buoyancy force. So this could be asked in the short question. The question would be, why is the measured weight within water less compared to the measured weight outside water? The answer would be because inside water, the buoyancy force is countering some of the weight. So that's why the weight measured inside water would be less. पानी के अंदर भारी से भारी चीज को भी आपको उठाना इतना मुश्किल नहीं होता. Okay, a block of material of unknown volume is submerged in water and found to weigh 400 Newton. Okay, in water. The same block weighs 700 Newton in air. Find the specific weight and volume of the material. Water ke andar weight hai 400 Newton, outside the water weight is 700 Newton. Okay, so we need to find out what is the specific weight and volume of the material. Okay, so basically formula hamare paas hoga would be this. Okay, you see here, weight in air will be equal to the weight in water plus buoyancy force. The buoyancy force was the one which was countering some of the weight. Okay, so if you add buoyancy force with the weight in the water, it will give you the actual weight. Okay, so this is one. So you have the weight of the air, weight in the air, you have the weight in the water in this question. So first of all, by using this, you can find out what is the buoyancy force, just subtracting the two. Okay. Once you know the buoyancy force, then buoyancy force is equals to gamma into V. Okay, gamma into volume. Okay, now volume, is it mentioned? Determine the specific weight and volume. No, volume we need to find. Gamma water is known. So gamma water is 9810. So we can find out what is the volume. The volume of the water displaced is 40.8 liter, which is 4.08 times 4 minus 2 meter cube. Okay. So if we know that this is the volume, then we can find out what is the specific volume of the block. Okay, specific volume of the block will be what? Gamma is equals to weight is equals to gamma into volume. So gamma is equals to weight divided by volume. As I told you, W is equals to mg, which is also equals to gamma into V. Okay, so that's 700 divided by the volume of the block. So you're going to get what is the specific volume. That's the solution of this problem. You can see this one. Okay, a metallic part is hanging by a thin cord from a floating wood block. The wood block has a specific gravity 0.3 and the dimensions of 50 by 50 by 10 millimeter. The metal part has a volume of 6600 millimeter cube. Find the mass of the metallic part and the tension in the cord. So you have a situation like this. This is a wood block. एक लकड़ी का ब्लॉक है, उसके साथ आपने एक तार अटैच की है, तार अटैच करने के साथ एक मेटेलिक ऑब्जेक्ट नीचे अटैच कर दिया. अब वुड ब्लॉक तो फ्लोट कर रहा है, तो वो साथ में मेटेलिक ऑब्जेक्ट को भी अपने साथ रख रहा है. Okay? तो नाउ द क्वेश्चन इज दैट दैट इज द मेटेलिक ऑब्जेक्ट का अपना वेट है, वुड का भी अपना वेट है, तो टोटल मिला के वुड ब्लॉक इज सबमर्ज्ड इन वाटर, नॉट कंप्लीटली, पार्शियली सबमर्ज्ड इन वाटर. ठीक है ना. एंड इट इज शोन हियर कि 10 मिलीमीटर अगर इसकी हाइट थी, तो 10 मिलीमीटर में से 7.5 मिलीमीटर तो वो अंदर चला गया वाटर के, 2.5 मिलीमीटर इज स्टिल अप. ओके, सो व्हाट डू वी नीड टू फाइंड आउट? वी नीड टू फाइंड आउट कि ये जो मेटेलिक पार्ट है इसका मास कितना है. व्हाट इज द मास ऑफ दिस मेटेलिक पार्ट. ओके, और ये जो कॉर्ड है, इन दिस कॉर्ड व्हाट इज द टेंशन? This is what we need to find out. Solution is one thing. We are going to go towards the solution, but first I want you to let me know, do you understand the problem statement or not? You have a wooden block, you have a metallic object. They both are connected via wire and put into the water. If the wire was not there, the metallic object would go down. But since it is connected with the wire, which is connected with the wooden block is floating. And so it is also holding the metallic object. Okay. But because of the weight of the metallic object and the weight of the wooden block, this wooden block, which has a height 10 millimeter, 7.5 millimeter, it is dipped in water. 2.5 millimeters is still up. Now, I mean, we want to know that what is the mass of this metallic object. Before moving over to the solution of the problem, first of all, do you understand the problem statement or not? Okay, the metallic object volume is provided. What is the volume of the metallic object? That is provided. Okay. And for the wooden block, specific gravity is given. Specific gravity for the wooden block is 0.3. Okay. So now let's see the solution. Basically, we have a situation like this. We have two things here. One thing is the wooden block. The other thing is the metallic object. Now, for the wooden block, we have the buoyancy force, which will be acting upward. And we will have the weight, which will be acting downward. And also the tension in the cord, because दोनों एक दूसरे को hold की भी हैं. तो cord के अंदर tension तो होगी, ठीक है? The tension in the cord, because this cord is going on the downward side, it's trying to pull the wooden block down. That's why tension is also on the downward side. Okay, so tension is also on the downside. So two forces on down, one force up, and this is in equilibrium because it's neither going down nor going up. Okay, so these are the forces. So we have a situation that FB1 will be equal to T plus W1. When it is in equilibrium, that means all the forces are cancelling each other. Okay, so we have this equation. So is this equation clear? T equals to FB1 minus W1, or you can say FB1 equals to T plus W1. Okay. Now let's talk about FB1, buoyancy force. Now this is the buoyancy force. So buoyancy force is basically gamma into volume displaced. Gamma will be for water. So water को displace कर रहा है. So gamma will be for water. So no issue in the gamma. Gamma is known. Volume displaced is how much? We can find out the volume displaced because look here, it is dipped 7.5 meter, 7.5 millimeter. And this is basically what, 50 by 50 by 10. So this 10 millimeter is this distance here. Out of 10 millimeters, 7.5 millimeters dipped. So basically, what is the volume dipped? 50 by 50 by 7.5. 50 by 50 by 7.5 is the volume of the block which has displaced water. Right? The remaining 50 by 50 by 2.5 is still above water. So as you can see here, so gamma into volume displaced. So volume displaced will be 50 by 50 by 7.5. So we're going to get what is FB1. Is the calculation for FB1 clear or not? Okay. T is unknown, W1 is unknown right now. Okay. So what is actual weight? But actual weight we can find out. Why? Because for this log, specific gravity was given. Specific gravity was given, and specific gravity for this specific gravity is what? Basically what? It is gamma of this log, gamma of this wood divided by gamma of water. So if we know this, we know gamma of water, we can find gamma of wood. Okay. So we know this thing. And if we know gamma of wood, then we can find out what is the weight, because weight is basically what? Weight is gamma into volume. Weight is equals to mg and it is equals to gamma into volume. Now gamma of the wood is known and volume of the wood is also known, 50 by 50 by 10. That's a complete wood. Okay. So 50 by 50 by 10 multiply by gamma, multiply by here by specific gravity as well. If you just include this formula into this together. Okay. So this thing is equals to, so we get weight 1, W1. So if we know W1, if we know FB1, we can find what is the tension in the spring. The tension in the spring is done. Till here it is clear or not? Okay. Now the next thing is that we need to find out for the metallic object. Okay, let's see the balance for the metallic object. Obviously the weight of the metallic object will be going in the downward direction, and we will have the buoyancy force in the upward direction, and we will have the tension in the upward direction. It's the same cord, but this cord is pulling the wood down and holding the metallic object up. So in reality, when we are looking with respect to the metallic object, the cord is actually holding it up. Okay. So tension will be acting in the upward direction for the case of the metallic object. So our equation will become what? T plus FB2 equals to W2. Okay, so this will be our equation. Now T is known because tension in the cord will not be different for the block and for the metallic object. It will be the same tension. It's single cord. Okay. FB2, we know the volume of the metallic object. It was given in the question. Multiply by gamma. Okay. So this will be the buoyancy force. Okay. For this object, FB2. So if we know the tension, if we know FB2, we can find out what is the weight. And if we know the weight equals to mg. So we can find what is the mass. The mass comes out to be 17.8 grams. So that's the solution of this problem. If anybody have anything which is not clear regarding the solution of this problem, you can ask. Let's have a break of 2-3 minutes till the exam going on. Okay, now let's discuss one application of this buoyancy is the hydrometer. Hydrometer is basically a device which is used to measure the specific gravity of the liquid. Okay, basically hydrometer is like its construction is similar to like thermometer, but in thermometer you have a small bulb. Here the bulb is a slightly bigger than the stem. In thermometer, how does the thermometer look like? You have a small bulb and then you have a stem. And the stem is calibrated, right? So you can see the temperature. So here you have a bulb, but this bulb is a slightly bigger bulb. And then you have a stem and the stem is calibrated. Okay, what we do is that we put this hydrometer inside any fluid. Okay, and then based on how much this hydrometer is dipped in the fluid, the reading on the stem is going to directly give us the value that what is the specific gravity of this fluid in which it is dipped. Okay, so it's very simple. Basically, how do we calibrate it? How do we use it? First, we take the hydrometer and dip it in water and see the reading, and we make it 0. Then we dip it in any other fluid. If it is dipping more than that, then that fluid is actually lighter than water. If it is dipping less than that, less than the mark of water, then it is heavier than water. Okay. So based on that, we can find out, and we can actually calibrate it at what would be the specific gravity of this fluid. Now, अगर फ्लूइड जो है वो हैवी है तो वो ज्यादा घुसने नहीं देगा ना हाइड्रोमीटर से, तो हाइड्रोमीटर की जो रीडिंग है वो कम आएगी. अगर फ्लूइड बहुत लाइट है वाटर के मुकाबले में, ठीक है, तो फिर वो ज्यादा अंदर डीप चला जाएगा, राइट? Okay, so small problem. A hydrometer shown sinks 5.3 centimeter in water. The bulb displaces 1 centimeter cube and the stem area is 0.1 centimeter cube, 1.1 centimeter square. Find the weight of the hydrometer. So we need to find out what is the weight of the hydrometer. Weight of the hydrometer will be equal to the buoyancy force. Why? Because normally when the hydrometer is dipped, eventually the hydrometer becomes static. means the weight is trying to pull the hydrometer down, but the buoyancy force is holding it up. So they both are balancing each other, and now it is stationary, static. So the weight of the hydrometer would be equal to the buoyancy force. The buoyancy force will be equal to gamma of water displaced multiplied by the volume of the displaced water. Okay. So the volume of displaced water will be equal to the volume of bulb plus volume of stem. The volume of bulb was given directly. This is the volume of the bulb. Okay. Regarding the volume of the stem, you have the area and you have the length, how much it is dipped. So the area is circular of the stem, and what is the length which is being dipped in the water. So that's 5.3. So area multiplied by Z. Okay, so you're going to get what is the weight of the hydrometer. Is this thing clear? Okay, next topic, stability of immersed bodies. What is a stability? Stability means a slight disturbance is not going to affect its orientation. Okay, so if I am stable, then if somebody if somebody pushes me a little, I'm not going to fall down. Okay, but if I'm unstable, then a slight disturbance is going to let me fall down. Okay, so this is how it is. Suppose if an object is immersed in water. Okay, now there are two things. There is weight of the object, which is actually acting in the downward direction, and then there is a buoyancy force. Since the object is immersed in water, there is a buoyancy force which is acting in the opposite direction. Okay, in the upward direction. So whether the object is stable or unstable depends upon the location of center of gravity and the center of buoyancy. Now here these two things are different. Look, there are three things that you should understand. One thing is the center of gravity. Then we have, I will say here, center of buoyancy. Then we have center of gravity, center of buoyancy, and centroid. Centroid. Three things. Okay, so you should be able to differentiate what are the three things. Okay, suppose if I have this object circular, the centroid would be the geometric center. Is it clear? Now suppose in this object we have some of the mass here. We have some additional mass here. So what will happen? The center of gravity now will not be at the centroid. Center of gravity will shift closer to the larger mass. Center of gravity will become here. So that's the center of gravity. So in this case, this is centroid, and that's the center of gravity. Now suppose this object is dipped in water till here. So the buoyancy will act on the center of the dipped object. Okay, so buoyancy will act in the centroid of this shape, which is dipped. So centroid of this shape might be here. So this will be the center of buoyancy. This was the centroid, and this is the center of gravity. Clear? Center of gravity depends upon how the mass is distributed. Centroid based on what is the shape of the object, irrespective how the mass is distributed. If you have a balloon and you put a little water in the balloon, centroid would still be in the center, because it does not matter how the mass is distributed for the centroid. It's a geometric center. But the center of gravity, it will be different, because it will be dependent upon how the mass is distributed. Where you have larger mass, center of gravity will move towards there. And center of buoyancy depends upon geometric center of the dipped object. So in this circle, if not the whole, if in this sphere, if not the whole sphere is dipped, so only the part which is dipped, center of that part would be the center of buoyancy, where the buoyancy force will act. Okay. So anyways, this is center of gravity, center of buoyancy, centroid. Okay. For the case of immersed bodies, since the whole body is dipped, so center of buoyancy will be the same as centroid. Center of buoyancy does not care how the mass is distributed. Centroid also does not care how the mass is distributed. Okay. Center of gravity, for this it cares. Okay, it depends how the mass is distributed. Okay. So since the body is completely immersed, so centroid and center of buoyancy would be the same. Okay, so now we have two things which will be looked upon. One thing is the center of gravity, the other thing is the center of buoyancy. Center of buoyancy and centroid are the same for this case. Okay, since it is completely immersed. Okay, now we have three conditions. If the center of gravity is above, so if the center of buoyancy is above center of gravity, then this object is considered as stable. If you produce a little disturbance in the object, there is a righting moment. Okay, so the righting moment is going to bring the object again into the same position. So suppose if you turn it a slight like this, or you turn slight like this, you will find that the C and G will move in a way that they are going to return back. The moment which will be produced because of their motion, because of the rotation or heel, is going to produce, is the righting moment, is going to return it back to the original position. So this is the stable condition. So for the stable condition, center of buoyancy is above the center of gravity. Now, if the center of buoyancy and center of gravity are same, this is when possible, when the mass is equally distributed. Then center of gravity would be in the center and the object is completely immersed in water. So the centroid would be the same as the center of buoyancy. So in that case, it does not matter. It is neutrally stable. Neutrally stable means if you tilt it a bit, just it will rotate until there is until the tilting effect is there. Okay, it will not return back to its original shape, or the rotation would not expel. Okay. Then we have another situation in which if the center of gravity is above the center of buoyancy, if G is above C, then this is the unstable condition. If you slightly tilt it, it will rotate about 180 degrees. Okay. So these are the three conditions for the immersed bodies. If C is above G, if G is above C, or if C and G are both at the same point. Memorize them for the short question. Memorize them for the short question. When a body is stable, when it is unstable, when it is neutrally stable. Is it clear? Now we look about the floating bodies. The body which is not completely immersed, it becomes a bit more complicated. Okay. Because now center of gravity might be different than center of buoyancy, which will be different than the centroid of that object. Okay. So we might have a situation like this for the floating bodies. Okay, for the floating bodies, what happened is that we define another term which is known as metacenter. Metacenter. Now, what is metacenter? Metacenter is like this. Suppose you can have a look at the ship here. This is an example. This ship is partially dipped in water. Okay, the center of gravity of the ship is G. Center of buoyancy is C, because center of buoyancy depends upon the volume which is dipped in water. Okay, And if you join C and G, you can have a line which is the line of action, okay, which is passing through point O. Now, if you tilt the ship a little, so what will happen? Actually, the position of C will change. The position of C was not changing for the completely immersed object. Even you tilt it, the position of C would remain the same because the whole object was immersed. So the center of buoyancy was the same as the centroid. So it was not changing. But here, when you tilt the object, part of it is immersed. So what will happen? Some part of it is going to come out of the water. Some part of it is going to go into the water. So even the shape of the object which is now immersed in water, once you tilt it, that shape, immersed shape, would be different. And so the center of buoyancy would be shifted according to the volume of immersed object. Okay. So you see here, if I tilt this ship like this volume has come out of the water and this volume has entered into the water. So now this side volume is a little less and this side volume is a little high. Okay. And so the value, so the center of buoyancy is going to shift toward this side. And this shifting of the center of buoyancy towards this side is going to produce the righting moment. So if you see here, I produce the moment in this direction, but the righting moment is in the opposite direction. Why? Because G is like this, C is like this, so it's going to produce a righting moment, which is opposite to the moment produced to tilt the ship. So in this way, the ship is going to return back to its original position. Okay, but the thing is that now how do we analyze the stability of the object? It becomes a bit difficult because C is also shifting. As we rotate, C is also shifting. So it's not the same position of the C. So what we do is that we find the two line of actions. One line of action was before the tilt was made. The other line of action is when the tilt is made. And the two line of actions are going to coincide at one point, and that point is known as metacenter. Then we find the distance between, then we find this metacentric height Gm, distance between G and M. G is the center of gravity, M is the metacenter. And based on this Gm height, we actually determine whether the object which is floating on the in water, whether it is stable or not. Okay. So there is a small derivation about it, but again, I'm not going to go into that derivation. Okay. Now, metacentric height, derivation of the metacentric height, you can go through it yourself. Again, it is using the second moment of area. So the end result is this formula. Gm is equals to I naught naught, which is the second moment of area, divided by volume, dipped volume, minus Cg. Cg is the distance between the center of buoyancy and center of gravity. Gm is the metacentric height, which is the distance between the center of gravity and the metacenter. Okay. So now for the submerged objects, if Gm is positive, the body is stable. If Gm is negative, the body is unstable. And if Gm is 0, the body is neutrally stable. Okay. So again, this thing, memorize it for short questions. You could be asked, what are the stability criteria for the immersed objects? What are the stability criteria for floating objects? So this is the stability criteria for floating objects. You have to look at Gm. Gm is the metacentric height. If this is positive, stable. Negative, unstable. 0, neutrally stable. Okay. Okay, there is a small numerical here, and with this numerical, we are going to end this topic. Okay, a block of wood 30 centimeters square in cross section and 60 centimeter long, weights 318 Newton. Will the block float with sides vertical as shown? This is a question. We have a block of wood and we put the block of wood in water. Okay, so we just want to know whether this block of wood in this condition and water, would it be stable or not? If it is stable means if I put a little disturbance on it, it will return back. But if it is unstable, then if I put a slight disturbance, it will flip. Okay. So I want to know whether this will be stable or unstable. Okay. So for this, first of all, what I need to know is how much of this block dipped in water. First, I need to know how much of it is dipped in water. So in order to find it, since I know that since I know what are the dimensions of the block. So it's basically 30 centimeter by 30 centimeter, and the length is 60 centimeter. Okay. So since it is floating in water, so equilibrium of forces, summation Fy will be equal to 0. So weight will be equal to the buoyancy force. Okay. So the weight of the block is provided 318 Newton. The buoyancy force will be equal to gamma into volume displaced. Gamma of the water is 9810. Volume displaced of water will be 0.3 into 0.6 into, we don't know how much it has been immersed in water, D. So if we just equate this equal to 0, we can find out that it is 18 centimeter immersed in water. So out of one side, which is 30 centimeter, 18 centimeter is immersed in water. Okay, now once we know this, we can find out whether this is stable or not. It is Gm equals to I not divided by volume of the immersed object minus Cg. Okay, I is the second moment of area, with formula for it will be provided to you. Okay, it will be a rectangle basically, AB cube upon 12. That's a formula. So just substitute the values. You're going to get what is the second moment of area divided by volume. Volume dipped. So 60 by 30 is 60 by 30 by 18, because we have found out that 18 centimeters is dipped in water. Okay, minus Cg. So it's G minus C. So if you look here, G will be the center of gravity of this object. So if this is 30 centimeter, G will be in the center, 15. C will be the center of buoyancy. Center of buoyancy will be the centroid of the dipped object. Now out of 30 centimeter, 80 centimeter is dipped here. So center of 18 will be 9. So it will be 15 minus 9. So just substitute the values, you're going to get Gm. Gm value will be negative, shows that it is unstable. A slightly disturbance is going to make it flip under this condition. Now, what should be the dimension of this block to make it stable or neutrally stable? If this is the question, it's kind of an extension of this question. In this case, what you're going to do is that you're going to now put this as 0, because for neutrally stable, Gm should be 0, or for stable, it should be positive. Okay, and then change the dimension. Okay, so let's say one of the dimension, change it and find out, let's say this 30 centimeter. I want this to be changed so that it becomes stable. Okay, so find out this thing, that what would be the value here that would make it 0 here. So you can find out that what would be the dimension of the block so that it becomes stable at this point. So that is a kind of an extension which could come in the exam. So with this, these are some of the homework problems. Okay. So you have homework problems for chapter number 1, chapter number 2, chapter number 3 combined together. That will be your assignment number 1 that you have to submit before midterm. Okay. Okay, the midterm exam is next week, Thursday, right? So I would expect that you submit me the homework problems by Monday. And on Monday, I will upload the solution of the homework problems on the Google Classroom, so that before the exam, you have the solution of all the homework problems with you as well. Because as I told you, in the mid-exam, it will be 20 marks. Out of 20 marks, 5 marks or less will be from homework. So you'll have a question of 5 mark or 4 mark or 3 mark from the homework. 15 or 16 or 17 marks will be from the lecture. Okay. Theoretical will be less than 30%. Numerical will be 70% or more. So that's the distribution. I've not yet made the exam paper myself, but nothing is going to come out from outside. Okay, so even the theoretical things, only the thing which I have mentioned during my lectures. Okay, these things can come in theory. Only those things might come. Okay, the homework problems are with you, and you will also have the solution of the homework problem by Monday. Since Monday you are going to be submitting your homework, so you can submit them. Okay, for the homeworks you can make it a group assignment. Okay, for submission purpose. Okay, so you are 24 students. Make group of 4 students. Okay, so 6 homeworks will be submitted to me. Okay, but on the homework assignment, just write the name of the group members. Okay, so this I'm doing just so that your manual work would be decreased a bit. But still, even if you are not solving a homework problem for submission, you have to go through it for the exam, because I told you a small part of it will be there from the homework as well. Okay. If there will be any changes in the numerical in the exam, the changes would be exactly the same as I have discussed during the lecture. Okay. So this is all about. So now at this time, you have actually covered the material till the mid exam. Okay. This lecture week 4 and 5 till lecture week 5 is the mid exam. Lecture week 1, lecture week 2, lecture week 3 is the first quiz, which you are going to have it on next week Monday. Okay. Coming Monday. So coming Monday, you are going to have your first quiz, which will be from lecture week 1, lecture week 2, lecture week 3. This is lecture week 4, lecture week 5, which will be included in the mid exam. Okay. On coming Monday, you're going to submit me your homework. And on coming Monday, I'm going to upload the solution of the homework problems. Okay. Anybody have anything to ask? So you can ask, otherwise this lecture is done. So we are done with fluid statics. From next class onward, means tomorrow onward, we are going to start with fluid dynamics. That's it for today.